the theorem says that if suppose S is an ordered set with the least upper bound property, upper bound property. And suppose B is a non-empty subset of S, B is a non-empty subset of S having, and B is bounded below. So, S is an ordered set which has a least upper bound property, and a set B has a property which is bounded below. Now, these together will implies the least relation between the greatest lower bound property. Okay. So, what it says is if B is bounded below and let L be the set of all lower bounds of B, then the supremum of B, that is the least upper bound of B, that is alpha, will exist in S, and this alpha will be the infimum value of B, that is it will be the greatest lower bound for B. And in particular, infimum of this V exist in S. Okay. Infimum, let us see the proof of this. What is given is S ordered set which has a upper bound property. Upper bound property means if any set is there which is a subset, non-empty subset of this, and if it has an upper bound, then the supremum of this will exist in this. Now, here we are assuming that S has a upper bound property and a non-empty subset B is bounded below. Then because of this upper bound property and this condition, we will show that B will have the greatest lower bound and infimum of B will exist in S. That is what is. So, since B is given, B is bounded below, this is given. Okay. And what is our L? L is the set of all lower bound of B. B is bounded below, it is already given. It means there is a bound available. So, L is non-empty. So, this implies L is non-empty. Okay. Now, L is the set of all lower bound of B. So, what is L? So, clearly since L is the collection of, L is the set of all lower bounds of B. So, basically L consists of those by, it means L is the set of those points in S, by in S, such that by is less than equal to x for every x belongs to B. Because L is the collection of a lower bounds. So, the by is set less than equal to x, then by will be the lower bound for B, and all such by which satisfy this condition will come in the class L. Okay, and this will be a non-empty set. This one thing is clear. Now, every x. So, if we look the L, L is the collection of those points which are less than equal to x for every. It means every point of B behaves as an upper bound for L. So, clearly every x in B is an upper bound, of L. So, it means L is bounded above, thus L is bounded above. bounded above. So, L is a non-empty set which is bounded above, it is a subset of S. L is a subset of S. So, bounded above and is a subset of S, is it not? S in order. So, we can apply the property because S is an ordered set having the least upper bound property. So, by the property, since S has a since S has least upper bound property, so by this L will have a supremum value. So, L has a supremum value, supremum in S, exists, supremum value will exist, and let it be, let alpha is that supremum value of L is alpha, suppose supremum value of this alpha is that. Okay. Now, if we choose gamma, if gamma is any number less than alpha, then gamma is not an upper bound of L. Upper bound of L, because alpha is the least upper bound. So, if we take any number lower than gamma, lower than alpha, then that cannot behave even a upper bound for L. Otherwise, gamma will be the least upper bound. Okay. So, gamma if it is less than alpha, it cannot be an upper bound. Hence, what is our B? B is the set of those points which are for such that every point of this is an upper bound for it, and here gamma is not coming in an upper bound for L. So, obviously, gamma cannot be a point in B, because all the points of B must be an upper bound, is an upper bound which we have shown, but gamma is not an upper bound of L, therefore, gamma cannot be a point of B. Okay. So, what this follows, it implies that alpha is less than or equal to x, alpha is less than for every x belongs to B, because any number less than alpha cannot be a point in B. So, alpha will be the least number and then alpha will be less than or equal to x. So, this shows that alpha belongs to L. Okay. That is what alpha belongs to A, that is the supremum will exist and it is in L. Now, if any number which is less than alpha, any number beta which is greater than alpha, then beta cannot be in L, because alpha is the least upper bound and all the beta is greater than. So, again it will not be in L. So, once it is not in L, alpha is not in L, beta is not, then what happened? That this beta which is greater than alpha, in other words, that alpha will be the infimum value of B, because then beta will be in which? Beta will be in B. So, it is a alpha beta. So, this shows alpha is a lower bound of B, is a lower bound for B, but beta is not, as if beta is greater than alpha, it will not be lower bound for this, okay, because it is the least. Therefore, alpha will be the infimum of B, and that proves the results. Okay. So, that shows the result. Now, having proved this thing, we will come back again to the sets where we are discussing the open sets and closed sets, etc., where the supremum value, infimum value will be required. So, we need basically we wanted to show that result where the supremum concept and infimum concept is required. So, that is why all these things were taken. So, this result we wanted to show, the result is let E be a non-empty set of real numbers non-empty set of real number which is bounded above, which is bounded above. Okay. And let by is the supremum value of E, that is least upper bound for E. Then the result says that by will be a point of closure of E. Closure of means set E together with its limit point is the closure set. Okay. Hence, by belongs to E if E is closed set. Okay. So, obviously, when E is closed set, E bar is equal to E. So, this result second part follows immediately, then nothing. The first part we wanted to show first. So, that E is a non-empty set of the real number which is bounded above, and supremum of E is B, suppose y, then y will be a point in E bar. Now, since E bar is a basically E bar is the union of E and E dash, where E dash is the set of all limits point, set of limits points of E, collection of all the limits points of E denoted by E dash. Now, if y belongs to E, if y belongs to E, y belongs to E, then obviously y will be the element of E bar, because it is a union of this and y bar. So, nothing to prove. So, let us suppose y is not in E, but y is a limit point of E. Assume, we will show then y is a limit point. So, assume y is not in E, but we wanted to show y is in E closure. It means y must be a limit point of E. So, that we wanted to prove. So, let us seek for every h greater than 0, there exists then a point, there exists then a point, say x belongs to E, there exists a point x belongs to E such that y minus h less than x less than y holds. Why? Here this is our set, say by E, this is the set E, the point y is not in E, it is outside of it. Then we can find for each h greater than 0, we can find at least some point which lies in the interval, say this is y, in between y minus h to y. This point x will always be available. Otherwise, if it is not so, then y minus h will behave as a upper bound for E, if it is not so, and this is true because otherwise y minus h will act as an upper bound, least upper bound for E, as a least upper bound of E, which is not true, because y is giving to be the upper bound. So, as soon as you take a number slightly lower than this, then this number must be available. It means, in between y minus n and y, one can always get at least one number of x E which is available. But what is the y minus y n? But this interval y minus h, is it not a where x lies? So, is it not a neighborhood of y with radius, say h? It is the left hand neighborhood, left side neighborhood of y in h. So, there exists a neighborhood of y which includes the point of x. It means every neighborhood of this y will include at least some point of E. So, this shows that, but this is the neighborhood, is a neighborhood of y with radius h, in which the point x is in E, in which there exists a point x in E. So, this shows that y is the limit point of E, because the definition of the limit point of the set M is every neighborhood around the point y, every neighborhood of y, however small radius may be, must include the points of E. And this is true here, that if we take any neighborhood of y, at least one point x is available. Otherwise, if it is not available, then it will contradict to the fact that y is the supreme value of E. So, if it is a limit point, then y must be the point in the closure A dash, hence y is in closure of this set. So, this proves the result. Okay. Now, remark we can see. We know if E is a subset of y is a subset of x. Suppose where x is a metric space. Then we have seen that a set may be open in x, may be open in y, and may not remain open in x. This we have seen just like a open interval a b, which we have seen, it is open in R 1, but it is not open in R 2. So, in case of the open set or closed set, the space which encloses the set is important, where the set is E is open. So, that is why we can introduce the concept of an open set relative to the space, relative to y or relative to x. So, we introduce here two definition, that one is a set E is open, a set E is open, subset of x, means to each p belongs to E, there is associated a positive number R such that the condition d of p q is less than R, where q belongs to x, implies that q is in E. Then we say E is open with respect to x. Open subset of x means then E is said to be open relative to x. Similarly, we can say by, since y is also a metric space under the same metric topology D. So, E may also be open with respect to y. Then we say define that the set E is open, the set E is open relative to y, by D or is a metric space by D if to each here also x d we will write x d is a metric space, okay, relative to x by relative to y if to each p belongs to E, there is associated an R greater than 0 such that the condition d of p q is less than R, Q belongs to capital Y, imply that Q is in E. Then we say it is a. It means what? Suppose we have this set X D, which is a metric space. A set E, this is a set E. We say it is open in X, means that if we take any point P in E, then one can always find out a neighborhood around the point P or a ball centered at P with suitable radius, say R, such that all the points inside this is a point of E, Then we say that E is open in all the points Q which are of X, all the point Q which are in X. If they are the point of E, then we say it is a open E. It means that every point is an interior point with respect to X D. But when you say this is our Y is a subset of X. So, it is also a metric space with respect to D. Then we say that E is open with respect to Y. Now, here when you draw the neighborhood around the P, then the point Q which you are choosing must be a point of Y, because you are not getting the point. Of course, the point of Y is also the point of X, but there may be some point which are in X, but not in Y. So, this relation, when the distance of P Q is less than R and Q belongs to Y, implies if Q is in E, then we say E is open in Y. So, as if there is no X, only E is a subset of Y and E will be the open set in Y. Every point of P is an interior point with respect to Y. That is all. Then we say E is open relative to Y, similarly E is open. Now, this has been shown that a set E may be open with respect to Y subset, may not be open with respect to the large set, and that examples we have seen. However, in case of the compact set, we will see this result, this restriction is not there. So, that is more friendly than our open set or closed set. So, that is the idea. Okay. So, we will see that. Before going for the compact set definition, we have one more results. That result shows what will be the form of the open sets in the relative case. Suppose Y is a non-empty subset of X, X D be a metric space, where X D is a metric space. Let X D be a metric and Y be a non-empty subset of X. A subset E of X, a subset E of X D is open. A subset E of X D, a subset E of Y. I am sorry. So, I will subset E of by D. Let it be by D. A subset E of Y. A subset E of Y is open relative to Y. If and only if E can be expressed as, or E can be written as Y intersection G for some open subset G of X. So, what this result says is, let X D be a metric space and Y is a non-empty subset of X. So, Y under the same metric D will also be metric space, and suppose E is a subset of Y, then we say a subset E of Y will be open with respect to Y or relative to Y if E can be expressed into this form for some open set G of X. If and only if, that is, if E is of this form, then E will be a open set subset of Y, and if E is open, then it can be expressed into this form. So, vice versa. Let us see the proof of this. Okay. Suppose E is open related to y. E is open relative to y. We wanted to show E will be of this one. So, by the definition of the relative to y means to each p belongs to E, there is a positive number say our R p such that the condition d of p q less than R p, where the q belongs to y, implies that q will be in E. This is by definition when E is open relative to y. Okay. Now, let us consider B p as the collection of all such q belongs to X such that distance from P q is less than R p, where q is in the elements of y. Let us q is in X. So, this is already there, q is in it. Let us see. Now, obviously, this is a neighborhood. So, once in neighborhood, it is an open set. And G, if I take the union of all these B p, where the p belongs to set E, then this collection of the open set will also be open. So, it is an open set, is an open subset of X. Clear? Nothing to. Now, since P is in the neighborhood B p, which centered P and radius say R p, P is in the for all P belongs to E. This is by construction because P is the center of this neighborhood. So, it is clear that E will be contained in G, which is G intersection y. Because this B p is a set in E, and all the points in E belongs to B p, and G is the union of B p. So, E, every point of E is in y as well as in G. So, it is intersection of this thing is obvious. By our choice of B p, we can say we have that B p intersection y is a subset of E. By our choice means because we have B p constructed like this way, set of all such that this is there is a positive such that this one is. So, when it restrict q to y, then all these points basically they are the points common to E, intersection with this and contained in E. So, by our choice, because this will be the set, to each p there is a positive because E is open, because E is an open set. So, this entire thing is available in E, because E is giving to be an open set relative to this. So, this is by our choice. Therefore, for every p, so the G intersection y, take the union of this, G intersection y is contained in E, and hence E will be equal to G intersection y. So, one result is complete. Conversely, just one more. Conversely, if G is open in X and E is of the form G intersection y, then every p belongs to E, has a neighborhood B p, which is totally contained in G, because G is open and E is of this form. So, E will also be for any p belongs to E means it will be in G, and G is open. So, neighborhood must be available in G. Then the G B p intersection y neighborhood intersection y will be contained in E. Okay. Because P is in there and G is this form. So, intersection will be available in E. So, that E is open. So, that E is open relative to y relative to y, and that is prove the results. Okay, thank you very much. Thanks.